All right, I'm just keeping it going. Hopefully get this recorded. You can probably see what time it is. It's 10:15. Our live class is starting in 45 minutes. I'm trying to get every minute I can. And we gotta enjoy some music, folks, right? I mean, if you're sitting here watching me do math in my living room, you can also watch me like jam out a little bit. Let's keep it going. Okay, so let's talk about now real gases. It was only like about a 30-minute lecture on this idea of ideal gases. And I do kind of expect that was mostly review, but if not, if there was some stuff that was unfamiliar, reach out to me. Let's talk to make sure that you're feeling good about your ideal gas stuff. Okay. So I expect this coming up, this part of this material is going to be fairly new for you. Okay, so number one, real gases interact. Okay. We also know, I forgot to put a point number two here. We also know real, whoa, let's try that again. We also know real gases have volume. Okay, but I'm not going to focus on that as much for right now. This is what we want to talk about. Okay, so real gases interact, and there's two types of interactions: attraction or repulsion. So in that last lecture, I was talking about attraction. Attraction through hydrogen bonding or through London dispersion forces. And the effect that attraction has on a gas is that it can actually make it compress when, of course, the container is free to move, right? In a rigid container, you'll just see a decrease in pressure. But if the container was not rigid, you would actually see some compression, some change in volume, okay? Conversely, repulsion, so if the interaction is not favorable, so meaning like maybe two positive charges repelling each other, that would result in expansion. Of course, if it was a non-rigid container. If it was a rigid container, it would just result in an increase in pressure. Okay? We want to keep this in mind. Attraction equals compression, repulsion equals expansion. And there is, as it turns out, a sweet spot. Okay? If I draw a potential energy potential energy diagram, and we're going to get used to seeing these types of diagrams. So I'm just going to say potential energy on this axis. And then this axis, I'm just going to call separation. And by separation, what I mean is like the distance between molecules or atoms. Okay? Our potential energy is going to look something like this. Okay? So there is going to be this region where the separation is small, right? So on this side of the scale, the separation is quite small. So that would give us repulsion. So that would give us what I called an unfavorable potential energy, so a large potential energy. As we'll explore in this class later on, we'll see that potential energy really wants to be minimized. If we can minimize our potential energy, that is beneficial. That's a favorable interaction. Okay? But now, if they're too far separated, right, they're maybe somewhere out here, okay, the potential energy is going to want to drive them to actually compress, okay, to attract each other, okay? So that side of the curve is attraction. And right here, this represents the sweet spot or their equilibrium position, if you will, the function of state. This is where the state would exist at that minimum, okay? And so we use the compression factor Z as a means of kind of telling us where are we at in this range, okay? So I'll define the compression factor Z as Vm, remember that's molar volume, intensive property, over Vm standard, okay? And so we remember that Vm equals V over N, And of course, Vm standard, or even Vm ideal, we know is with 4 sig figs 22.42 liter per mole. Okay? And so there's a couple different ways that we could calculate what the compression factor is, right? We could say, well, if we know that V over N equals RT over P, this is just doing some algebra with the ideal gas law, okay? That, if I plug in STP conditions, so I'll put a standard and a standard, then I get this Vm standard, okay? So that's right, 273 and 1 ATM, that I would get that 22.42 liter per mole. So now that means I can say, well, then the Z, because Z is Vm over Vm naught, then that's going to be P, and I'm not going to put standard, this is just whatever the pressure is, times Vm divided by RT. Okay? So, right, keep in mind, now this P and this T are just whatever the observed pressure and temperature are. Okay? And, wait, did I say that? No, I said that wrong. Excuse me. Okay. Because, yes. Excuse me, those have to be the standard. Apologies. Now, this molar volume right here is going to be the molar volume as a result of whatever the pressure and temperature is. Okay, right? So go back to this. This Vm will be nRT over P. This Vm standard will also be nRT over P. But one is at standard conditions and one is at whatever the other conditions are. Okay? And so another way to write that would be P Vm equals Z RT. Okay? So now we have a few things to consider, right? Because if you think about this, right, if Z is equal to 1, then we just have our perfect ideal gas. Okay? And so as it turns out, this is typically in a low pressure regime. Ideal gas is typically low pressure. Okay? When Z is greater than 1, let's think about this for a minute. Okay? So this means when Z is greater than 1, this molar volume, this observed molar volume, is greater than the 22.42 liter per mole. And that would mean expansion has to be going on. Okay, so we'll say that would be expansion. And so the result of that could be from repulsive forces dominating. And that's going to be from high pressure, right? Because under high pressure, we'd be forcing all these molecules to get together. And perhaps they don't like that. We're forcing them to get too crammed together. So they're going to want to separate. And when Z is less than 1, okay, this molar volume right here has to be less than our 22.42 liter a mole. And so that means compression is going on. Okay. And I'm going to call this moderate pressure, kind of somewhere in the middle. And so here attractive forces are dominating. Okay. Oh my gosh, I'm sorry, you guys. I'm getting my nomenclature wrong. You're probably all freaking out like, at 2 minutes, I don't know what we're talking about. So let me just make sure we're still on the right algebra here, right? Standard, right? So to go from here to here, all I did was just a little bit of algebra, right? Okay, just to make sure that we're on the same track. And keep in mind, right, I didn't put the standard here on this molar volume or on this molar volume because that indicates whatever the observed molar volume is, okay? So again, when Z is equal to 1, when the compression factor is 1, that's an ideal gas. When Z is greater than 1, there are repulsive forces dominating, so the particles are like being forced to get close together, so that's high pressure. And so when Z is less than 1, there's attractive forces dominating, right? It's influencing those molecules to occupy a smaller volume than the 22.42. And as it turns out, that's like moderate pressure. So we'll put more quantitative qualifiers on that as we go. Okay.